started. Thanks everybody for coming. This presentation is Keys Under Doormats, Problems and Solutions for Storing Credentials in Web Apps. My name is Ron Craig. I work for IBM. My colleague here is Dmitriy Beryoza, and he works for Vectra. Vectra AI, specifically. He's a security researcher there. Really sharp guy, I know, because he used to work with me over at IBM, part of the ethical hacking team there. His expertise really, at that time anyway, was in reverse engineering, whatever kind of stuff you guys tried to make up to make sure that they couldn't get the secrets. You always failed, he always figured it out. My job is mostly to set standards for secure engineering. I also manage their incident response, so when we find vulnerabilities in software and so on, try to make sure that we fix all those things and let customers know where the fixes are. Disclaimer, our opinions are our own and not those of our respective companies, and we make mistakes, so we're hoping that this material that we give you will be very useful. If you use it at your own risk, caveat emptor, etc., etc., etc. And here's our agenda. We'll talk about secrets, just a brief introduction. We'll talk about some of the incorrect ways that you've probably all seen people try to store secrets, and then ways those can be abused. We'll talk about the proper ways of storing them, safeguarding your master key, and we'll talk about what that is in a moment. And actually a way of storing that in the file system that is still pretty resistant to most of the classic vulnerabilities that you see that allow people to exfiltrate files from your application. And then finally, we'll talk about a open source project that will help you with that. And then some key takeaways. The slides will be put on a GitHub site, and you'll get the link to the GitHub site on the last slide, so you got to stick around for that. And let's get going. So, almost all of your apps, you wouldn't be here if you didn't have to store secrets, and every modern app has them. User login passwords, of course, credentials to your back-end systems, to your database, and to microservices and so on. Encryption keys, so if you're smart and you've got sensitive data, you're encrypting it in a database. Doing application encryption, you need a key for that. Private keys for your certs. Keys for API client secrets and so on. Sensitive customer data, like I was saying, for the in the database, perhaps. And the key is, of course, all these things have to be securely encrypted both at rest and in transit. Don't forget, if you're subject to GDPR, there are enormous fines involved if you screw this up. And if you're using extremely sensitive data, like from the NSA guy, try to keep it encrypted or at least heavily obfuscated, even in memory. So let's talk about a few terms so we're all on the same page. A login password is, when I use that term, it's something that a human uses to get into the front end. You sign into your bank, you sign into this web app. Credentials are secrets, oftentimes username and passphrases for databases, but sometimes they're other types of credentials. And for that, it's something the system uses to access another system. Two technical terms we use is a data encryption key, or DEK. That's the key used to encrypt whatever secrets your application is trying to protect. They might be keys, but they also might be passphrases for a key store or whatever. The other one is the key encryption key. I'll just probably use the term master key because it's faster to roll off the tongue. And for us, that is the top level key, and it's used to protect the data encryption key. That's the only thing that it encrypts. All your secrets are encrypted with the data encryption key. At some point, we'll pause and talk about why in the world would we introduce this extra level of indirection. But the key thing here is we're talking mostly about credentials rather than ordinary login passwords, because you all know those need to be stretched and salted and hashed and all that stuff. Lots of places you can find out how to do that. All right. That said, in the experience we've had with testing applications, we've found a lot of insecure ways, and you've probably seen these too. We've seen this quite a lot, putting your key right in the source code. That's always lovely. Putting in plain text in config files, or if you are a certain big blue company with a large application server and you decided that obfuscation is plenty and you put that in a configuration file, you can go to Stack Overflow and find lots and lots of people's configuration files with that information still in it because they forget it's there and they think it's secure, and it's not. You can go online and find something that will quickly unobfuscate that stuff for you. Plain text in databases, and seriously, we see this, boggles the mind, and in environment variables. And this is something that you see people say a lot. Oh, well, you know, in our pipeline, we're going to keep things secure. We're not going to store it in the repository. It's all going to be in environment variables. Yeah, try to keep those away from him. It's not going to work. And then people will say, well, all right, we're going to do some obfuscation, and they try to get extremely creative, like using base 64. Nobody will ever figure that one out. Or they will, like that big blue application server, go and XOR with a static key that no one will ever figure out. It took about 10 minutes, I think. Or they do really decent encryption, but then they stick the key right in the source code for anybody to pick up. Well, people can't get my source code. Oh, yeah, they can. So why is this a problem?
Well, just curious, by the show of hands, how many of you recognize these patterns in the code that you've worked on in the past? Okay, okay, so quite a lot. Just curious, of those who raised their hands, how many actually put it or saw it being put in production code that actually went out the door? All right, so those with their hands up, please write down your names and your names you're reporting it to your management.
It's very common, very common. Oh, you got them all fixed. So his company is okay. All the rest of you guys. All right. So plain text, sensitive data can be leaked from the application in a whole bunch of ways. And yes, I don't care how much time you spent into obfuscating it. Anybody can invent a system that they can't break. Inventing a system that somebody's really extra skilled can't break is much more difficult. If the data are encrypted, but the keys are right there, you can still get access to the data. If they're hard-coded, then what do you do if there's a breach? We need to put out a patch to all of our customers because it was, oh my God, what a mess. You can't rotate them, you can't change the keys, all that good stuff. And how can we abuse this? Well, first of all, you can do code analysis. We can steal the source code. Dmitriy was telling me that there was a study, a bunch of IT people were interviewed and said, how much money would it take for you to offer your source code to someone? And the going price for your company's source code is $150 on.
Well, to be fair, it was a fairly small percentage that agreed to that price, but those people do exist.
I don't need many copies, I only need one copy.
Yeah, exactly. Yeah, that's true.
Yeah, we need their names too. We need to know that you can reverse engineer the application, and you know, obfuscators are great, but there are ways around those. Just go to DEF CON and you can see lots of ways. Leaking files through vulnerabilities, and this one is the one that we see most often. Path traversal vulnerabilities. They're grabbing the key store there. If I've got the key store and I can get the key, no problem. Local file inclusion. Somebody's grabbing your config ini file, which has got all those lovely secrets that you so carefully, lovingly base 64 encoded in there. And it continues. XML external entities. Here we go. We're grabbing some private key files. That's quite easy to do. And we see it way more than I'd like to admit. SQL injection. Fine. We'll load the whole plastic file, get the whole customer database. Oh, it was encrypted. And this table in that column contains the key for all the encryption. Okay. And then here's leaking your environment variables. Folks may not realize that the environment variables are actually in the proc file system on Linux, and sometimes we can just go grab that. So there's all the environment variables that you thought were so secure. And that's hardly an exhaustive list. But notice something about these, because it'll be important in a minute. If I want to steal a particular file, I do need to know what the name of the file is and what the path is to it. And what will I get? I will get the contents of that file, which usually is all you need. But it makes you think, is there a way around all this so that even if you have all these things, you still can be secure? Well, so this is where we came up with the keys under Doormats, and incorrectly stored encryption keys and credentials become your keys under Doormats. I don't know if anybody recognized the key on the first slide. Anybody recognize what company makes that funny looking key? It's a Bloy. It's a great lock maker, great security. But of course, if you throw it under the doormat, it doesn't do you a lot of good. And so we will see data that's not encrypted, or is encrypted poorly, is encrypted properly, and then the key stored someplace close by. Or the one we're really concentrating on and trying to solve here is vulnerabilities that allow file exfiltration to allow retrieval of the encrypted data and the key that's used to encrypt it. In other words, you didn't lock the door, or you locked it and you put the key someplace close by. Let's talk about some of the right ways to do these things. First of all, no plain text storage for data or keys, and obfuscated is plain text. No obfuscation, no custom-made encryption. We see this happening, and there's no reason for it in today's world. Keys,
just
yeah.
to refer to something, Bruce Schneier is a renowned cryptographer. You may have heard about him, and there's something called Schneier's law. It basically states that anyone can make up an encryption algorithm that he himself cannot break, or perhaps his friends cannot break. You can try it as an exercise. You can probably come up with an algorithm that you yourself cannot break. But what is really hard is create something that, you know, years of analysis of top cryptographers in the world will not break. And that's what we're up against. Often when you're facing these threats, if you encrypt your data with the algorithm that you yourself created, and let's say a nation state tries to break into your application, they probably have enough skilled people that will break the algorithm that you came up with.
Yeah, so I, for example, when I was 11 years old, I wrote a letter to the NSA, and it was all encrypted, encoded, encrypted. I thought it was really clever. I still work for IBM, not the NSA. Apparently they weren't quite as impressed. So it's easy to fool yourself, but it's much tougher to fool everyone else. Here's a really important one. Please generate the keys fresh for each install. If you are in your build process generating keys and you're putting them into every install image, then every customer you have has the same keys. And all I have to do is break one, and now your entire customer base is compromised. I've seen it from companies that I've worked for. It's embarrassing, frankly. Don't hard code, because again, if there's a breach, what are you going to do? You can't, you don't want to have to issue patches for this. You need to be able to change these keys. Oftentimes too, auditors will say, oh, you've got to rotate keys, so you need to change this key now after a certain period of time, and there's no way to do that otherwise. Use encrypted key stores and vaults. They're there for a reason. And they are pretty decent at what they do. The catch, of course, is the passphrases that are used to secure those. You need to have a way of securing those. All right, and then, of course, this is for the login passwords. It's got to be hashed, salted, and stretched. Stretch just means you give it a factor for amount of work that has to be done so that you slow down offline attackers. And so essentially, we've got to store data in such a way that an attacker who gets an encrypted copy of it is still screwed. They can't do anything with it. So Kirchhoff's principle says a crypto system should be secure even if your attacker knows absolutely everything about the system except for the key. And the guy from the NSA who was talking said, do the same thing for your entire system. Just assume everybody knows everything there is to know about your system and exactly how it works, what all the endpoints are, and then you've got to secure it anyway. So, and our goal here was to design a way that full exfiltration of the code and all the encrypted data still does not cause an information compromise. So is that
Actually, no, you can do this one.
I can do this slide too? Okay. So are we back to square one? We've got this problem. So our credentials have to be stored in a password-protected key store. Our sensitive data has got to be encrypted in the database. And for that, you need a key. And we use, the term here is a data encryption key. You can use that. I've actually got little routines that you feed it a data encryption key, and you feed it an alias, which doesn't have to be secret. And it takes the two things and does some hashing together in a cryptographically secure way and generates a passphrase, a nice long passphrase for your key stores. You can use that to encrypt database data and so on. So the data encryption key is the one that sits above and protects all of your secrets. Then what we suggest you do is have an additional key, the master key, that encrypts that. And so, AES 256-bit encryption of that. If you don't have the master key, you can't do anything with that. Because you can't do anything with that, you can't get the rest of the secrets, right? So now, what the heck are we going to do with the master key? Deja vu, turtles all the way down, key of the key of the key of the key. So if you store it in plain text or you hard code it, you're going to be right back to the same problem you had before. And now all I have to do is steal your data, the key store, data encryption key, and your master key, and they've got everything. They've really got to get the master key if you do this right. And with that, I'll turn it over to you.
All right, thank you. Thanks, Ron.
Smart guy here who's going to solve all the problems.
Sure. So we have this problem. We really don't know whether master keys can be stored safely. And many development teams don't know either. They give up at this point. This is what we've seen in the past. They have good cybersecurity hygiene. They've encrypted all their secrets, but they're faced with the same problem. Like, I have this master key. What do I do with it? And a lot of them actually give up and just embed that key in the source code. So here you can see that they're actually working with a key store, but the key that opens that key store is hard-coded. So we're back to square one. And as Ron mentioned, if files can be stolen, then so can so can the master keys. All your data can be revealed. So is there a way to store it securely? Actually, there is. There are actually multiple ways of doing that. Well, here are some of them. First of all, the very secure way of storing the master key is not storing it at all. And you probably have seen it in different applications. There are, for example, hard disk encryption applications that ask for a passphrase when you boot up your machine. And if you don't have that, you're done. There's no way to recover your data, or at least no way that's going to take a reasonable amount of time. And some smartphones have the same model. Like, we've seen all this trouble with FBI trying to unlock latest models of iPhones. They use the same system. The password that user enters serves as sort of this master secret that the key is derived from. If you don't have that, and you don't have any other technical ways of getting at the data, then the data is locked out forever. Unfortunately, as web developers, we know our applications have to run in unattended mode. They may be rebooted at random periods. So having a human operator to enter the master secret is most of the time is not an option. So that doesn't work.
Yeah, so I had an application like that was in production precisely one day, and then at 2:30 a.m. it had to be rebooted. And so by 11 a.m. the next day, there was then a stash file for the key phrase sticking right there on the system too with everything else.
So another industry recommended way is to use hardware security modules. Those, of course, are specialized hardware devices that they store encryption keys in hardware. Those are dedicated boards or devices you put on your server rack. And to interact with them, your application basically talks to an API and gets the key it needs. That means that to be able to get at that key, attacker needs to have code execution privileges in the context of your application. And if they have that, then it's game over, because they already can do everything your application can do. So there's no protection against that. The problem is that these systems are not cheap. And they're not universally available. Like computers are getting better at getting secure enclaves and some type of hardware measures put in, but it's not, they're not universal. There are different technologies and different platforms, and they're not available everywhere. And also these devices are not cheap. Like last time I checked, they run into thousands of dollars, so not everyone can afford them. There are, of course, software equivalents. Some of these measures are built into modern operating systems, and also third-party implementations exist. But you also kind of have the same problem. It may not be available for your particular use case, and there are costs associated with deploying and managing them. There are also key lifecycle management systems. Same idea. They're responsible for the full life of the key from birth to safe destruction. But again, this is yet another system you have to manage, you have to kind of configure properly. So it's, depending on your use case, it may not be a good option, it may not be cost effective for you. So we tried to think of kind of a universal low cost way of storing master secret on a system. Because as I mentioned, sometimes your requirements, your business requirements, the costs are just too prohibitive. It's not possible to have a dedicated system just for managing the master secret. And are we really stuck in this case? And we think that that's not the case. There actually are ways to store and derive master keys based on unique characteristics of the system your application is running on. So essentially, we think that master keys can be derived from system features that are hard for a remote attacker to determine. If you start thinking about this, there are probably a number of different unique identifiers that come to mind. First, network card MAC address. That's an easy one. Unfortunately, there are a bunch of problems with it. It's usually broadcast on the network, so it could be leaked. Portions of it depend on the manufacturer. So I think it's a 6-byte sequence, and the first few bytes are actually assigned to the manufacturer of that network card. And also, it's a really short sequence, so key space is really small, could be brute force. Motherboards have IDs, hard disk drives have IDs, CPUs have IDs. Again, key space may be small, some parts may be manufacturer dependent, and in that case, they could be guessed. And this is something that may be difficult to depend on in a virtual environment. If you have a virtual machine that's migrated between physical servers, if you have your Docker installed where Docker instances are being brought up, shut down, these things could actually change for the context of your application. So it's something hard to rely on. Disk volume name, again, key space may be small, and this is something that may be leaked through just exfiltrating Unix files. So these are not, in our determination, these are not good candidates for being used as something to derive master secret from. And also, these IDs are not intended for this purpose. We know that encryption keys have to be generated in a cryptographically secure way. They have to be truly random. And so there's little or no entropy with these IDs. And to make things worse, even if you wanted to make them secure, most of the time it's not an option. You're not going to go and check and change your hard disk drive ID. So then we thought that there must be a way to actually store the master secret in the file system somehow. But at the same time, it cannot be stored in a file that can be known by name. And, well, specifically because there are too many ways to steal files. And just storing it in a file, that presents an opportunity for someone to steal that file. So this is what we're trying to avoid. So we came up with a group of methods that store master secrets by utilizing features of the file system. And we're going to outline two such methods that we think are easiest to implement. So the first one is storing master keys in secret folders. If you think back to what Ron mentioned, the file exfiltration vulnerabilities that we referred to at the beginning of the presentation, they all have several things in common. Well, first of all, they all steal file contents. But the contents is the only thing they can get at. They don't give you any information about file metadata. And another common thread is that you have to know the name of the file you're stealing. And also, like, even if you don't know the name and try to brute force, it has to be brute force in a reasonable amount of time. So let's say there's a name plus some counter added to the name. If you can run within reasonable time, you could brute force the name even if you don't know it exactly. So what we suggest is actually storing master keys in a subfolder with a randomly generated name. And the folder is generated when you install your product on the system. So it has to be unique in each particular install. Otherwise, as Ron mentioned, if you compromise one customer and figure out that name, it'll be the same for all other customers. The folder name has to have a prefix by which it can be recognized. Otherwise, it's kind of hard to tell which folder is which. So basically, let's say you have a configuration folder, and inside you build a folder with a long random name and a prefix which you can recognize it by. And then inside, your keys are stored as regular files. And application can easily find the folder and load the keys. You can just do a search on the file system, and if you come up with a name that has that prefix you're looking for, you can find your keys. If you're paranoid, you can make things a little more obfuscated, but the idea remains the same. Of course, file and folder permissions have to be set in such a way that another user cannot enumerate that part of the file system. So let's say you have multiple applications running on a server. You're protecting your master secrets this way in application A. If there's a vulnerable application B, that user under which it runs just happens to have full read writes on the file system, attackers could use that angle to enumerate the file system and figure out the folder name to look for in the first application. So the permissions has to be set in such a way that it will only be accessible to the user that runs your application and the root user. And as I mentioned, you basically just search the folder with the prefix that you know and load the keys that way. Attacker does not know the folder name. The folder name is long enough to make a brute force attack impractical. And to be able to get at that folder, attacker really needs to have capability to search files in a file system. That usually comes with just code execution privileges. And if that is the case, then nothing really will help you. Like if they already have that kind of capability on the system, then it's already a full compromise. And they could, if you were to use a hardware security module, they would be able to talk to that as well.
How is this different from storing the key in a registry or as an environment variable?
I know the name of the registry.
How do they, like the same way they know this key, right? They should know how to get to the key, because the application should know how to get to the key.
Well, registers are Windows only, right? Those are the registers you refer to. Depending on the user you're running under, like we've seen applications run with root privileges. Registry hives are stored in the file system. Conceivably, you could try and get at those. But that's an interesting use case. Environment variables on Unix, if you can steal files in the context of the application. Ron referred to a case earlier. On Unix, environment variables are stored in a file under that process context. So by exfiltrating that file, we've done it in the past, so we know that for sure. By exfiltrating that file, you will know those environment variables.
So, and we know the name of the file is /proc/environment.
Yeah.
Read that file, you got it.
Okay. So another approach is a little stealthier. It's storing master keys in file timestamps. So key, several bytes in size, can be distributed of timestamps of multiple files created for this specific purpose, or existing files. So basically you have your configuration folder, then the folder for storing your master secret, and then you have a set of files in that folder with a prefix that corresponds to that particular key, sequence numbers, and some random parts so that they cannot easily be enumerated. The application can interrogate timestamps easily. You can just search through the folder. But attacker does not have access to file metadata, usually. If they do, most likely they have code execution privileges on the system already. Again, if you're paranoid, you can make things a little hard to deal with for the attacker. But again, the principle remains the same. So let's say you have a key that's 32 bytes in size, and you choose to store 2-byte chunks in timestamps. You'll need 16 files to kind of distribute those bytes over. And the files themselves can be empty, or maybe just some random garbage to throw people off the scent a little bit.
I love giving hackers a headache.
And of course, multiple sets of files have to be created to store multiple keys. And I'll show you how it actually looks like in a moment. And as I mentioned, the file names can indicate which key you're talking about. And so you can have a prefix or suffix. And to indicate, because these should be ordered sets, they should either have a sequence number in the name, or maybe they could be sorted alphabetically. It's your choice, really. So here's an example. So let's say you have a file on the system that's the timestamp 30th of August, and this is what it looks like in hex. It's a modification timestamp. If we wanted to store a key, let's say for simplicity's sake, it's 6 bytes in size, we can create 3 files, take 2 bytes, write the bytes in the timestamp with our values. And as you can see, the timestamps still remain kind of sane, but we have now stored little bits of data in the timestamps of files. There are caveats that come with this method. It's more complex, and as a result, it's a little more fragile. Some of the file systems do not guarantee consistent setting of timestamps. Like we've tried this on Mac, and you set a particular timestamp, and when you read it, it's a different timestamp. Apparently, they do not support, or at least in Java, where we tried it, a modification timestamp does not support consistent setting of milliseconds. So if you choose this as your method, it's better to use second granularity or above, seconds, hours, etc. Also, recommend changing only a portion of the timestamp. It may be tempting to just, the timestamp is 8 bytes. Hey, that's the 8 bytes I'm going to use. That can lead to really crazy timestamps. If you create timestamps that are, like, say, 15 years in the past or in the future, there's no telling how the operating system will react, or the applications on your machine will react to that. They may get, there may be bugs that will be exposed through that. So it's better to stay with sane timestamps. For us, 2 bytes per timestamp starting at second granularity was kind of the sweet spot. And there are certain dangers. So you have to back up. If you use backup and restore utilities, theoretically they could mess up the timestamps, so that way you will lose your key. So you have to be careful in that regard. And also, sometimes I see administrators running utilities like touch globally, and that would change the modification timestamps. So that can mess you up as well. So you have to be careful with how you employ this system. So actually, a good practice generally, if you have a master encryption key that's safeguarding a lot of customer data, on a properly designed system, if you lose that, you lose access to all your data, because that's the intent, that if somebody steals the encrypted data, they shouldn't have a way to get to it without the encryption key. So it's probably a good idea to back up the master encryption key somehow. There are probably many other ways of doing this. Feel free to experiment. There are probably other features of the file system we haven't thought about that you can try. And general goal is to kind of find that middle ground between being completely insecure and hard-coding your encryption keys and going with a HSM solution that's kind of expensive, or similar solutions that kind of require additional management, additional time and expense. So that's kind of the middle ground for the applications that cannot yet afford to go to the full-blown hardware solution, which is, by the way, the preferred way. This is kind of a poor man's version of the HSM. So the goal is really to utilize a method that's resistant to a variety of vulnerabilities, especially file exfiltration. Ideally, it can be defeated only by attacker gaining code execution privileges on the system, because that's the end anyway. It has to be low cost. That was our goal. And this solution, as you can tell, is free for you to implement. And it has to be reliable in the presence of system changes. So if something that runs on your system that changes the file system in such a way that you lose your master key, that's not good. You have to be aware of that. So we created a small library that we open sourced. You can scan the QR code to get to that repo. And the copy of the slides, Ron mentioned the copy of the slides, we'll post it as well. We implemented both techniques there. Feel free to play with it. It's in Java, so it actually plugs into Java security infrastructure. We designed it as a Java security provider. And these key stores, because they're really key stores, essentially, are implemented as key store class implementation. So it kind of fit the paradigm nicely. We welcome bug reports, feature suggestions, pull requests, whatever. Oops, sorry. Okay, and feel free to fix things and contribute. We structured it in such a way that Java implementation isn't in its own subfolder. I can imagine someone doing this for Node.js or PHP or Python. Feel free to contribute your own version if you feel like it. So the key takeaways, as we've seen in a lot of cases, and by the show of hands as well, it's very common to store secrets insecurely. And special attention must be paid to do encryption and secure key storage properly, because there are many, many mistakes that you can make in that area. And wide variety of vulnerabilities exist that may lead to full system compromise, especially if you can allow attacker to steal files. Master keys usually suffer from the same problems, and currently recommended methods of master key storage are mature and they're great, but not everyone can afford them. They're not probably a good fit for every type of application. So the method that we propose can be as a stopgap measure, and you can graduate to a more mature solution later on. And basically by using Unix system characteristics, in our case, file system, you can really improve security of your keys inexpensively. So we're at the end of our presentation. We'd like to acknowledge our colleagues that helped us with this. OWASP wants you to scan the code and rate the presentation. Let's see how we're doing on time. Yeah, we have some.
So one thing I wanted to mention too is why do we have a master key on top of the data encryption key? I said I would explain why that is. One reason is because if I need to change the key due to a breach or something, it's very easy because all the master key touches is the data encryption key. If I need to change the master key, rotate it, I just decrypt the data encryption key, get a new master key, re-encrypt. I don't have to, if you only use one level, if I have to change that key, I've got to go find every secret on the system that was encrypted, decrypted, re-encrypted, and that way leads to madness. The other thing that's nice to have this decoupling is your application may already exist, and you already have a data encryption key. You just need to secure it better, and it's very easy to plug this in. You don't have to change a lot of code. It's one little spot. All you're messing with is the data encryption key. If next week you become rich and famous and you're going to use an HSM and you want to change that, it's very easy now because it's a little tiny piece of code. You can use an HSM to secure your master key. So those are two really good reasons.
First of all, really good talk, and I really like the way you're hiding things. But I have a couple questions. It feels a little bit like security by obscurity to me, and it's not even that obscure because somewhere you're going to have code that's checked in that says where to look at, where to get the bytes out.
Right, and I'm telling you, the code says find my configuration folder. Now, open the file system, and iterate through the files till I find the file that's the right name. But you don't know what the right name is. I don't know what the right name is. The one on that system is different from the one on that system. So it's not obscure as to what the process is we're doing. I'd be happy to tell you what the process is, but as a remote attacker, you can't get to that information. The only way you can get to that information is run code on the system that has permissions in that folder to be able to find and figure out what the heck the file names are. Because if you don't know what they are, you can't ask for our flawed application to deliver their contents to you. Make sense? Yes, you had your hand up first.
So to continue that question, your first example with the folder name, where you add random information to the folder name, how does the application know what folder name to look for?
It doesn't. It says, in Java, it's files.get files, and it gives you a file list, and then you can say, do a filter, and here's my filter, KDK_splat. And it will give you back a list of files now, which you can get as an application. The attacker has no way of getting that list. Now you can walk through and say, oh, that's the folder. Now I can open that folder. I can do the same thing for the files. I'm looking for key number 1. Give me splat.key1. It'll give me a list of those particular files. But just because you know that's how I do it, doesn't mean that you can do it, because you don't know what the names of those files are unless you have remote code execution capabilities and can actually run that same code. Yes, sir?
So if somebody misconfigures the system, and they have a directory listing on or your web folder, they can see all of your files, and all the obscurity is gone.
That's
Well,
true.
It's
except
not code execution, it's just a misconfiguration.
True, and we should probably add it as another case. That's not very common, but it does happen. I agree with you, and so that is a possibility.
But the catch is too that if you do an LS, you're going to get a little bit of timestamp. You're not going to get the timestamp that's going to give you the right bytes that we need to regenerate the key.
But you could brute force
First
it.
case is just your first case when you just put that in the file. The secret is in the file name.
That's true.
Does no good.
That's true.
Yeah, but remember, like if you look back to the list of vulnerabilities that allow you to exfiltrate files, there are a lot of them, a lot of different ones. This is a particular type of vulnerability, and I agree with you. It does expose you, but it's just one type, not as many. Right.
Do you have any thoughts on tying this into configuration automation and deployment systems? You know, as part of your pipelines, deploying this out. Like, have you guys looked or done any of that work?
I would say that since this is going to be happening at install time and later, and it's going to be happening for protecting the application secrets, there's really not a lot to do with the configuration, unless you're talking about trying to hide secrets that is done in your CI/CD pipeline. That's what you're thinking about? I haven't thought about it yet. It's a good idea.
Yeah, so adding on, like, I don't want my developers or deployers to have this hard-coded anywhere in the pipeline as well, because it's the master key, right? So that's something to look at.
Okay.
So one thing when you said about hardware, I kind of like the idea because there's no way for an attacker to know what that is. But I understand your point, which is that it is easy to enumerate. But what if you took a combination of different hardware pieces and also took the most random values of that? So I'm sure they're going to have the prefix, which will be standard across all their devices. And the ending, let's say 4 digits, would be the unique ones. So take that for like 4 or 5 different pieces of hardware, and then make it as a 0-1 on the first folder name to know what pieces you are using.
Well, because of this. So people use that for fingerprinting systems, right? So if I want to recognize the difference between this system and that system, that's one way that's very common to do that. We see people do that all the time. Using that for cryptography, I think is, it looks random to you and me, but it's not really nearly random enough. Even if you take those pieces of data and you put them together, if I know what pieces of data you're taking, and I can steal each one of those because each one of those we talked about leaks, and I put them together in the same way that the application.
Or they're random, not random enough. You know, not random in the cryptographic sense of the word. You know?
Yes, but again, so the argument or the pitch, because I'm going to take this back to my team, so I'm thinking of questions that I'm going to get. Okay, so the only reason we're saying take this approach is because the attacker has access to download, has arbitrary file download. They can download any file from your system, but that's all they have. They do not have remote code execution.
Right.
They are not inside of your infrastructure.
Right.
So if they're not going to set up my infrastructure, they're probably not going to have my hard drive information, they're not going to have my CPU. So they're not going to have the full fingerprint to figure out where it is.
Well, there are two things here. So first of all, I'm not a Linux expert, quote unquote, but I know that on Linux everything is a file, right? So there's some of this information that may be stored in an actual file on a Linux system. That's point number one. Point number two is these things, like when we talk about random bits of those IDs, you probably have to go back and study how those IDs are actually created and assigned to those hardware devices. What may look random to you and me, in the cryptographic sense, may not be random enough, right? And a really skilled cryptographer may actually come up with a way to figure this out in a reasonable amount of time. So
You are correct, but the preface, the fundamental assumption that we are making in this whole approach is they don't have access to the system.
Yep.
So even if they figure out the logic behind it, they will still need to know, have access to the system.
But my question is, why would I take a risk in generating what may be a poor random value when I can generate what I damn well know is a fantastic random value with my secure random number generator and just use that?
And you cannot rotate that.
Yeah,
If you're using your
If you do
hardware,
that and I go and
you can't-
change your CPU or we move
Exactly,
to another
that's where
machine,
it's
you're
like-
broken, you can't get to your data.
You're tying it down to the hardware and now like have a dependency there, even physical or virtual.
Yeah, if you have then a policy that says you have to rotate your keys once a year,
Yeah, but, so I'm worried more about that changing the time step and I'm screwed.
Right, right.
I
So you could use the folder name, that won't change,
You
right?
could use the folder names instead. That technique works. Make sure that you use the M time, because M time is only going to be changed if you modify the file. Don't use C time. People want to do that. Don't use A time. Those are too fragile. M time will hang around for you pretty well.
And
Yes,
also another thing is that, like we're talking about these things looking like they're random, key space matters. So if they're random, but the search space is not big enough, somebody could just try and brute force their way into your system. If they can execute requests quickly enough and the space is small, they could actually succeed that way. So that's another consideration.
Very important.
Yeah, so use a real random number generator or a key gen out of Java to generate a real good value. Yes, sir.
You're using a folder with random name. I'm wondering whether you're using a file with random name.
That's another way. That's another way.
Or if you're me, you do both. Even if I'm using timestamps, I still randomize the name of the folder, I randomize the names of the files, and I stick it in key stamps because I'm just that paranoid.
So have you thought about using multiple applications on the same server with multiple keys and how these applications can recognize their keys versus other?
Well,
Yeah, so like your config folder in your application conceivably is in the sub part of the file system that belongs to your application.
Yeah,
so
it's
you can
not-
have
it's not an enterprise
thousands of
wide
them
management
all over the place, right? Yep.
Yeah, so one of the things that like traditionally seen is that the master key is stored like only like system administrators or people with excessive like privileges have access. Now, if you have this approach, does it open the code that knows where the key is stored to developers too, so that the developers can get to the master key in some way and then decrypt information?
only if the developer's got access to run code in your deployed system.
And also, remember this, that we alluded to this a little bit. I hope I understand your question correctly. The application, like if you store that master key, let's say under root privileges, and only the root user can get to it, then how does your application get to that file to read the master key? There's no easy way. It has to be readable for your application, and that means that if somebody has path traversal vulnerability in your application, then they can also get to that file. So,
But only if they know the name.
right.
And we don't know the name.
Thank you guys, that's all for the questions. You can reach out to Ron and Dmitry
Yeah.
afterwards.
We're gonna stick around. Yeah.